Welcome. In this session, we'll look at some examples that indicate how we can recognize infinite limits. The basic idea is that non-zero over zero is infinity, so to speak. But since we distinguish between positive and negative, we have to be a bit more careful. With rational functions, very often one-sided limits are definitely infinity or negative infinity, but the signs might be different on different sides. So I'll first state how we can recognize infinite limits for one-sided limits. So if we have a function which is written as a fraction f over g, with the numerator f having a non-zero limit, denominator g having a zero limit, and if the fraction f over g is positive for all numbers which are a little bit greater than a, so some interval from a to b is there in which f over g is positive, then the limit of f over g as x approaches a from the right will be infinity. If everything else is the same, except the fraction f over g is negative in the interval from a to b, then the limit will be negative infinity. The reason is that if you divide some regular number by numbers which are getting smaller and smaller, then the fractions will get larger and larger. So if there is no lower bound to the denominator, there will be no upper bound to the whole fraction. So the limit is infinite. Now, for algebraic functions, the signs cannot oscillate indefinitely between positive and negative, which means that for the fraction f over g will have a fixed sign in some interval from a out to some b, which may be very close to a, but there will be some definite interval. So for rational functions in particular, non-zero over zero will have infinite one-sided limits. Of course, similar recognition principles hold for left-hand limits as well as for two-sided limits. So if we have f over g, a fraction where f has non-zero limit, g has zero limit, and the fraction is positive in some interval that's contains a and is except possibly of course a, and goes on both sides of a, then the two-sided limit will be infinity, so on. Of course, you need to be able to recognize when a fraction is positive. In practice, that means you'll be doing it only for very simple fractions. So let's take one which is linear over linear. We'll talk about nonlinear inequalities near the end of this chapter, and you can combine it with this for more complicated functions. So we are finding the limit as x approaches 2 from the right of x minus 3 over x minus 2. As x approaches 2, x minus 3 approaches 2 minus 3, or negative 1, which is non-zero. But the denominator, x minus 2, approaches 2 minus 2, which is 0. Now, if I take any number that's a little bit bigger than 2, in fact, any number between 2 and 3, let's say 2.001, then x minus 3 will be negative because x is less than 3. But x minus 2 will be positive, which means the fraction is negative. This tells me that the limit is infinite and negative, so the limit is negative infinity. Let's do another one. This time we will do the limit as x approaches 0 from the left of the greatest integer function divided by x. So again, we want to look at numbers which are close to 0, but a little bit less than 0. For such numbers, say negative 0.001, the greatest integer function will be negative 1. So the limit from the left of the greatest integer function at 0 is negative 1. The denominator x has limit 0, so I have non-zero over 0. Okay. So to recapitulate, between negative 1 and 0, the greatest integer function over x is negative 1 over x. So we recognize the limit as being infinite. Negative 1 over x, if x is negative, will be negative over negative, which is positive. So the limit will be positive infinity. You have to be a bit careful. Just because the denominator has limit 0 doesn't mean the fraction has infinite limit. It's important that the numerator not have limit 0. You should always check that. If it's a rational function, of course, it's something we have done before. You reduce the fraction. What if it's not a rational function? Let's do the limit of the greatest integer function over x, this time from the right at 0. If I take a number between 0 and 1, the greatest integer function is 0. So the function is 0 over x for any number between 0 and 1. So its limit is actually 0. So hopefully these examples illustrate enough of the ideas behind determining when limits are infinite. So I'll stop here and we'll talk about infinite limits in the next session. Goodbye for now.